Okay, today I'm very glad to be here to talk about geometric deep graph learning. Okay. We know recently this large language model has becoming very popular, and people trying to extend this large language model to do various things. That's because this large language model has many good properties like homogenization, which can be adapted across diverse applications. You also have this emergence property that can be trained to get into this new capability like doing zero-shot learning. So how about a graph model? Right? Graph model still has unique strengths of capturing relation among entities. So the large language model cannot really replace graph model because it is non-trivial for large language model to understand graph structure and perform multi-hop reasoning. So a natural question to ask that, can we also build graph foundation model similar to this large language model? So we can train a graph model for one application, and then it can be generalized or adapt to other applications. The difficulty we encountering going toward that direction is that because the different graph really have different structure, so it is difficult to generalize. So a natural question to ask is that, is the current GNN-based representation learning powerful enough to serve as the base architecture for foundation model? So we know graph is everywhere, right? You can have this internet web, right? You can also have this protein network. You can have co-author network. You can have the social networks, right? They're all network. But in reality, besides saying they're all network, their structure are really quite different. And also, the graph has this non-Euclidean structure. Nowadays, graph neural networks are becoming the de facto standard for learning on graph. And then there's a variation of this graph neural network. And those graph neural networks really model the graph in the Euclidean space. So this representation learning, basically you have a graph that you have many nodes, right? We're trying to map each node into a low-dimensional Euclidean space. And then if the two nodes have similar embedding, then it indicates that their network similarity. And this can be used for node or graph classification, link prediction, node clustering, anomaly detecting, those various applications. And this graph neural network is just basically different way, okay, all those variations when we are aggregating in its neighbor, because the way this graph neural network capturing the network structure is by doing aggregation around your neighbor. So it's capturing the network structure really is at a very local level. It's not really at the global level, saying that what is the structure of the graph. And then, so if you look at a graph, right? So the densely connected area, their embedding is supposed to be close. Okay, that is what we want to achieve from this graph embedding. And so today, our focus is on talking about the representation space of graph. And then we want to address the issue whether the traditional Euclidean space representation is appropriate. So in the graph, there are various types of structures, right? For example, hierarchical or tree structure. There are actually, we have a metric of what we call the delta hyperbolicity, which we can measure the tree likeness. So the smaller the delta value means the structure is more closer to a tree. Okay, so a tree is a delta hyperbolicity value is 0. For the hyperbolic space, their measure also is a very small number. For Euclidean space, this delta measure actually is infinity. And for the graph, people are quite familiar with, like the DBLP graph or Twitter graph, their delta number is actually quite small, like 2.5, 3.5. So we know that generally this hyperbolic space is better aligned with this hierarchical structure than this Euclidean space. And then if the graph have this cyclic structure, that will be better represented by hyperspherical space. Okay, so basically, no, we talk about these three different space, right? In the bottom, in the middle, it is what we call this Euclidean space, which has a curvature of 0 because it's basically flat, right? So it is good to represent grid structure. And then if you look at the orange one, right? So that is actually the hyperbolic space. So it is good to represent this tree structure, and that has a curvature of -1. And on the left, right, the purple one is the spherical structure. It has a curvature of +1, and then it's good to represent cycle. And then certainly the computation in the different curvature space are different. So you can see that even we just talk about a distance measure, right? In the other geometric space is more complicated than the Euclidean space, where Euclidean is flat, so easy to calculate. And certainly, in this graph neural network, we always do neighborhood aggregations, and so that's basically an addition operation. You can also see the addition operation is far more complex. So the Euclidean space basically is flat, so we say the curvature is 0. And the other space, like hyperbolic space or spherical space, they are what we call curved space. And the curvature basically is a measure of the extent of how the manifold deviates from being flat. If you look at the volume of the space, the volume of this Euclidean space grows polynomial with respect to the radius. But the volume of hyperbolic or hyperspherical space grows exponentially. So given a dimension, hyperbolic or hyperspherical space is able to accommodate more objects. Or you look at the other way around, that we can use a lower dimension embedding to separate the points. So let's look at an example of this world map, right? So the Earth is a sphere, right? So, but we can map the map from a sphere to two-dimensional Euclidean space. But then there will be some distortion because the region near the north or south pole will be enlarged. And there exists no mapping between Euclidean space and spherical space that will preserve the distance. So in this talk, we really want to introduce generic geometric space to deep graph learning. The geometric space has emerged as an exciting alternative to the traditional Euclidean space. And it's got certain advantage. You have this superior expressiveness. For instance, any tree structure can be embedded in two-dimensional hyperbolic space with arbitrary low distortion. But the distortion is not bounded in even high-dimensional Euclidean space. And there are also many solid theory developed in the mathematical domain that, like the differential geometry or Riemannian geometry. So we can use this kind of theory, and then also there are many tools we can borrow to analyze the graph. Oh, the distortion is measured by the curvature. Okay.
And you're using delta as So you're basically using delta as
that is for the hyperbolic space, right? But all those geometry has certain curvature, so it's basically measured the deviation from the flat, okay, surface.
What I mean, you've got a graph embedded inside of some latent geometry. So these are points with distances in between. How do you measure curvature?
We map it to such a space. Right? We map it to a curvature, so you map it onto a sphere. Okay, so all those points they are not randomly located. They are just like we look at the other examples. You're mapping them onto a sphere, so the sphere has a curvature. Okay. So this geometry deep graph learning that they also impose some challenge because as we just showed you before, this addition is more complicated, right? So the aggregation is non-trivial. Also, we like to use Gaussian distributions, right? Gaussian distribution is also rather complex. So in here, certainly the computation is more complicated, okay? And then also the curvature of on the edge is not differentiable. So that also creates some problem to apply it in deep learning. And the mapping between different space is problematic in optimization. Okay, so there will also have a problem that also metric to Euclidean space is impossible. We cannot preserve the distance. Okay, so we're going to talk about in this talk the various issues of mapping into this geometric space. Okay, so we have published various papers on this topic. Okay, so we first talk about this graph model fundamental, right? So the first issue we want to address is that why we want to have this heterogeneous curvature, okay? Because as we said before that the different graphs have different structures, right? Some may be more like a tree structure, some may be more like a hyperbolic, like a cycle, okay? But it's more than that because even within a graph, the different parts of the graph may have different structure. But we can do a product of different space. For example, if we take a product of this hyperbolic and spherical space, then we get something in something like this, right? Okay. So basically, that is what we call a mixed curvature space because it consists of two different spaces, right? So when we want to modeling a graph, right? Certainly the traditional thing is the Euclidean space, but then we can also just map it into a hyperbolic space to capture the hierarchical structure. And this hyperbolic space is a homogeneous curvature, right? Because the whole thing has a curvature on -1. But we can also do a product space. The product space, then you have a mixed curvature. That will give us even more superior expressiveness and support, as we will say, that it can support contrast learning. Okay. So if we look at the graph in the bottom, right, in the bottom left, you can see that the blue nodes represent really a tree structure, right? And the red node represent a cyclic structure, and the black nodes, they represent a mesh which is fully connected. So different parts of the graph, they are really different, right? So if you use a single curvature to represent the graph, it may not be ideal. So we really want to allow a mixed curvature space to represent the graph. And then the right-hand side is a real social network. You can also see they have two different cluster. Right? You can see the structure is also different. So if we allow this mixed curvature space, actually is that in the graph that now every edge we can have a different curvature, which is referred as a Ricci curvature. Okay? So traditionally, when you represent the graph, we only have this adjacency matrix, which is just 0, 1, whether the two nodes are connected or not. Now you actually have an additional information is that the curvature. Okay? The curvature can either be positive or negative. And the positive curvature actually represents those nodes should be grouped together because they are close. And the negative curvature means that they should be separated. So this is very useful information if we want to do clustering. And then also from this curvature, we can actually derive this forward Ritchie flow and this backward Ritchie flow. Forward Ritchie flow can describe this particle movement. They are moving follow this flow into clusters. The backward Ritchie flow really is describe a kind of structural involvement where edges can be added to link the densely congregated area. And the multiple geometry space really facilitate us to do contrast learning. Okay, so let's look at some example. For example, we look at this three knowledge graph, and then we represent it as a product of this hyperbolic space and spherical space. Okay, so you can see that this one of the knowledge graph, that free base actually is quite different from the from the other two knowledge base, right? Because this because you can see that if we look at the hyperbolic curvature, right? The free base curvature is about much smaller than the WordNet and Wikipedia, right? Because it's only 0.3. The other is more 1.2, right? And then if you look at the spherical curvature, the free base one actually is much larger because it's like a 1.1 and the other is only around 0.2. If you look at the weight coefficients, right? So the free base also has a much smaller coefficient on hyperbolic space and much larger coefficient on the spherical space. So even we are just talking about knowledge graph, they are not necessarily very similar because different knowledge graph can have a different kind of structure. Like the free base is less hierarchical tendency than the other two knowledge graph. If we look at very different type of application, for example, like site-seer is a citation in graph, right? And the L-port graph, certainly they are totally different. So you can also see they are represented quite different. Here we decompose them as a product of two hyperbolic space multiplied by two spherical space and one Euclidean space. In here you can see that if we look at the hyperbolic space now, because different part of the graph, their hierarchical structure can be different. Right? One can be much deeper than the other part, so we can have different curvature. Okay, and then the L port, you can see the hierarchical curvature is much larger than the site-seer one. So the mixed curvature Riemannian space, right, representation can provide us a powerful way to quantitatively describe the graph structure in a succinct way. So that is good, right? Because this can shed light on a new direction for building graph foundation model because we know that the target domain and source domain, how different are their graph structure. Okay, but certainly trying to exploit this mixed curvature space also they are challenged because the Ritchie curvature is not differentiable. So the Ritchie curvature and Ritchie flow cannot be used in deep learning. So our solution is to develop a surrogate differentiable Ritchie curvature to support forward differentiable Ritchie flow and backward differentiable Ritchie flow. So let's look at some example on why this is useful to map the graph into this mixed curvature space. First, let's look at the case of when we do not have external label. If we want to do traditional graph neural network, right, that will need a lot of label. But if we don't have enough label, then the alternative is to to use this contrast learning, because the contrast learning can explore similarity of data among themselves, right? And not requiring external label. But however, it is non-trivial to obtain meaningful graph augmentation. This is very different from the CV environment. CV environment is very easy. You can change some of the pixels or color or things like that. Right? The graph one is more challenging. But however, if we have this multiple curvature space, then we can actually treat each curvature space as a view, and then we can do this contrast learning. Okay, so in here we have this graph, so we decompose that into multiple curvature space. Then we can do contrast learning, okay, among the different curvature space. Okay, so that will give us better results. So you can see that in here, right? We are not having the label. We are only doing this self-supervised learning, but it will be better than we do supervised or self-supervised learning in Euclidean space, and also will do better than the supervised method in this homogeneous curvature space. Okay, in sense, we do not compose into multiple curvature space. We just map it to a hyperbolic space. And also, you can see that if we map it into more components, right, we use more curvature space, then and certainly we are doing a final representation that can also improve our results. Okay. So another situation, for example, we look at a noisy graph. The traditional graph neural network is assuming that the graph is clean, and then we do this neighborhood aggregation. But if the graph is noisy, then we need to do this graph structure learning to purify the graph. Okay? So currently, all the graph structure learning is focused on the structure refinement. But actually, for noisy graph, both the edge and the node feature can both be noisy. Okay, so that's what we need to address now when we map them into this mixed curvature space. Okay, so basically in here we want to explore this Ricci flow, defined by this Ricci curvature. The fundamental challenge here is that, as we mentioned before, that Ricci curvature is not differentiable. So we formulate a differentiable surrogate of Ricci curvature, and then activate this backward Ricci flow. So this backward Ricci flow, you can think about it as a kind of structure involvement, where edges are added to link the density, that densely congregated component. So in here, we jointly refine the structure and the feature. So we refine the structure with backward Ricci flow, and we refine the feature by geometric contrast learning using this different geometric space. Okay, so you can see that when we are doing this, that our self-supervised learning method will be better than other self-supervised methods, but also comparable than most of the supervised method. Okay, so what we just talked about is this classification. But if you look at node clustering, we also do better. And if you look at some ablation study below, then it's also because we can capture this feature refinement. So another thing is that we want to look at this motif. This motif serves as the fundamental building block and play an important role when we talk about we want to classify graph. But in this, when we do this traditional GNN type of approach, then we don't really take this motif into consideration. But in here, we can actually consider the motif together. So we can use a generative adversary architecture which is able to generate motif in the graph and support contrastive learning to learn the curvature. Okay, so you can see that this our self-supervised approach actually is better than the corresponding supervised approach in the Euclidean space, and then you can see that with this motif considered, right, we better than both supervised method in Euclidean space and supervised method in homogeneous curvature, single curvature space. And this is previously is on linked partitions, right? But it also is true for node classification. And then again, you can see that when we consider more number of spaces, that will get better. And also an interesting thing to notice that even in the Euclidean space, if we want to consider motif, it doesn't really give it's the blue one, it doesn't give too much performance improvement. But in this Riemannian space, if we consider the motif, that will give us a very good improvement in performance because it is more natural to consider them together. Okay. So next we look at graph clustering, right? So first we're looking at how do we employ this edge curvature. Okay. So as we said before, that in the mixed curvature space, we can have rigid curvature on every edge, and then the positive curvature group nodes, and then the negative rigid curvature separate nodes. So this is an additional information to help to guide us how to form cluster. In the traditional approach, when you only have this 0-1 adjacency matrix, then the way we do graph partitioning is to minimize the number of edges connecting the two clusters, right? Okay, so again, given a graph, we decompose into the product on multiple curvature space, and then we use that to help us do the clustering. Okay, so you can see that we can do much better than whether it's the traditional deep clustering or traditional or clustering method. Okay. And then one of the advantages is that because we're using the curvature, so we can identify the hard boundary node, so and give it a different weight, so they will help us improve the performance. Okay. Okay. So the next thing we're going to look at is this irregular shape, okay, to form a cluster, right? You can see the picture, right, which consists of three different types of cluster. So this is very irregular shape. So traditional clustering method is very hard to deal with this kind of problem. But in here, we can, in the mixed curvature, we can explore this forward Ricci flow, as we said before, that this Ricci flow can mimic the movement of points into cluster. So we're not trying to identify this cluster boundary. We're just moving the points into these three different clusters. And this Ricci flow, we can use this ordinary differential equation to solve it. Okay. Okay. So actually, this is a very general method because it's not just applied to graph. Actually, you can apply to the image, text, or point, because for any of the other application, we can just create a KNN and connect graph. Right? You connect each point to its nearest K neighbors, right? So all those things can be converted into a graph, and we can apply this method. And you can see that I will use this point data set because you're easier to see that the irregular shape. So for ordinary clustering method, this very difficult to address problem. Right? But if you look at it, if we use this our approach, right, then you can see the result is much better than any other method because our MMI is in the around 85, right? But if you look at all the other methods, they are only in the 30s range, right? So they are much, much lower. The only exception is the deep reinforcement learning that give a close MMI number. But however, its ACC number is much lower. It's only 20 compared with close to 70, right? So you can see the power of this mixed curvature space. Okay, the reason we can handle this, as I said before, is that because we are exploring in this forward Ricci flow. So you can see that we can flow it on the left, we can flow into 3 clusters, and on the right, we can just flow into 6 clusters. Right? Okay. So another challenge in doing clustering is that usually we need to know the number of clusters, right? But this is challenging because in real good situation, we often don't have any idea of how many number of clusters is here, okay? But in hyperbolic geometry, it is related to structural entropy, okay? So the hyperbolic partitioning tree can be exploited for graph clustering with unknown number of clusters. According to information theory, the optimum partitioning tree in this hyperbolic space, right, can be obtained by minimizing the structural information. But the problem is that the structural information is not differentiable. So it's not being introduced in the deep model. But in here, we can formulate differentiate the structural information surrogate, right? Then we can use it to learn the optimum partitioning. And basically, we're using it as the objective function. So you can see that when we first map the graph into this hyperbolic space, right? And then we do this partitioning without the number of clusters as input, right? And this is some real examples, right? So the color is represent and the label. So in the rightmost, this one you can see that almost every cluster have the same colors, right? And the football one, they are also 90%, or they are in the correct cluster, right? So basically you can see that without the number of clusters, the method in this mixed curvature phase actually is better than all the other traditional approach, given the number of clusters. Okay, so the next thing we look at is this graph dynamics, right? So we are going to look at both the offline learning case and the continual learning case. Okay, so in reality, the graph is keep on changing, right? You have node being added, edge being added or deleted. So this embedding will change over time. Okay, so we want to find this stochastic embedding, and we can do that in this mixed geometric space. So you can see that the result is much better than the traditional approach. Certainly, the result depends on the curvature we choose. But the curvature actually is a time-varying thing. So if we look at this physics data set, you can see that in 1996, right, the rightmost one, it is spherical. It's much closer to a spherical data set. Right? But by 1998, it's still spherical, but the curvature is reduced. And then by 2000, it actually become a hyperbolic. And by 2002, that is much the hyperbolic curvature is larger means the hierarchy actually grow larger. So that looks very interesting, right? But this actually is true for any collaborative co-author data set, whether it is a physics data set or DVLP or archive data set, right? They all show similar tendencies, okay? The reason is that the availability of the World Wide Web has democratized the collaboration in academia. So it breaks down the barrier of communication and enabling research to collaborate effectively and efficiently across geography, disciplinary, and institutional boundary. I remember when I first started, like in the doing collaboration with other people, though, in the 80s, right? We only writing down on a piece of paper, you fax it to your collaborator, and we talk over the phone. So this kind of collaborator is very ineffective. So you can only have a very small group of people, right? So this is much closer to a cyclic structure. But now, with the World Wide Web, with this social network, right, it's much easier to a larger group of people. You know, they can collaborate together, and there usually is a structure there. So we are having a much bigger collaborative group, right, with a deeper hierarchical structure. Okay, so we can add different snapshot, no, or we can we can do an analysis. So for any current instance, we can use the previous snapshot, no, or as to do contrast learning, right? So we can, but certainly those things are on different geometry space. So comparing them, there is certain challenge there. Okay. So you can see that whether it's for link prediction or for node classification, no, by capturing the evolving curvature, we can do much better than the supervised learning. In here, because we have different curvature space, right? This is over different time period. We can use that to do contrast learning. So we do not need label. Actually, we can also do better than the supervised learning. Okay. Now we look at previously we're talking about is this offline learning. Now we talk about this continuous learning. Existing in continuous graph learning only work in the Euclidean space. Okay, and the self-supervised learning is needed for this particular case because as the graph evolves, we cannot keep on having new label every time the graph evolves. So we need to learn and adapt the curvature for each coming graph. As we see before, this curvature change is not only the number, it can also show change from this spherical to hyperbolic, right? And so we need to address this issue. There's another problem that the self-supervised learning in the traditional geometric space, when people do that, they will always have the problem of catastrophic forgetting. So we need to also handle that problem. Okay, so basically we use the teacher-student model. So the previous knowledge is accumulated in the teacher, and the current period, is the student model. We try to learn the curvature, right? So of the current graph, but we also use the teacher model, which remember the historical knowledge to help us. Okay, so with the two together, right? So we do this. Again, we can do this contrast learning without the need of the label. Okay, so you can see that our results through self-supervised learning without the label can do much better. Right? Here again, you can see that this archive graph, right, the changes over time, and then we can see that we can learn a good curvature estimation because our distortion measure is very small. Okay, so finally we look at some application. So the one application is recommendation. We know that in the recommendation, the popular recommendation method is what we call collaborative filtering. We look at each user, right, and then connect the user to the product is interested in. So this is like a bipartite graph. We have a user item graph. The edge is what people purchase or what people like. Certainly, this bipartite graph changes over time, so we can look at this. So there is this graph evolvement issue here, right? But when we map it into a different geometric space, right? But the user and item, previously when we do this in a Euclidean space, then we just treat them all similarly, right? But actually, the user and item, they have different properties, right? So item, because they are connected more through a knowledge graph representation, right? So they show more hyperbolic tendency, and the user connection is more cyclic, so it's more spherical. So we represent user and item in two different geometric space. And then but the connection is from user to item. So when we do the aggregation, we certainly have a challenge because the two things are at different geometric space. Okay, so but by taking care of this problem, then okay, so so sorry for the. So by taking up this problem, that you can see that our performance is much better, right? On doing the recommendation, and also you can see that because in this geometric space, right? So we don't need a very high dimension embedding compared to this Euclidean space. Okay, so another example we're looking at is that people can join multiple social network. So we can looking at this user alignment and community alignment. Okay, in here, if you look at it, for example, we have this DBLP database. We also have this A minor database. So basically, they are different way on showing co-author, right? So we are trying to do alignment between the author and the community from these two different network. And then you can see the alignment looks pretty good, right? Okay, so whether it is the user alignment or it is the community alignment, see, by mapping them into this geometric space, we're going to do a much better job. Okay. So this is the various publication. Okay, so today basically we talked about this geometric deep graph learning, and then we can see that it outperforms the deep graph learning in this Euclidean space. If we look at this classification and link prediction, we don't need external label, but we can do better than the Euclidean methods with label. We do self-supervised learning compared to their need label doing this supervised learning. For clustering, this geometric deep graph learning, we can handle irregular shape cluster, and also we can handle unknown number of cluster. Number of cluster not necessarily need to be an input. For this dynamic network, we can learn the involvement not only on the node embeddings, right, but also on the curvature. So we can capture this involvement of the structure explicitly And then we also look at this application like recommendation, cross-network alignment, right? Because we can handle user item with different geometric representation, right? So we can actually do better. So let's go back to our original issue of graph model as foundation model. Right? Our experience that we generalize the graph model within specific type of application. For example, if we have a recommendation system trained on buying music, that is not that difficult to fine tune it to become a recommendation system for book. Okay, because this kind of thing they are similar. Or if you have a recommendation system trained in the U.S. market, you want to open another store in Japan, so you can generalize this model to a different geography. Okay, those kind of things always reasonable or limited success, right? But if you want to generalize this graph model to totally different and domain, for example, from molecular domain to social network, that usually do not work. Right? So one of the reasons is that because their structure are quite different. And this geometry, deep graph learning does provide a way to explicitly, model the structure with this mixed curvature of Riemannian space. So we think that the future of this graph mining will relies on this geometric deep graph learning, and may be able to build this graph foundation model more closer. Right? Okay, this is the end of my talk. Thank you.
Wow, wonderful talk. It's a very solid and rich. And first, let's welcome thank Professor Yu again, and then we can have a few minutes ask questions. I think that lots of people have questions, right? We need to learn more. Okay. Any question?
So could you explain how do you calculate the hyperbolic curvature and the spherical curvature on the different social network?
Oh, this basically is you're learning it. I think it's more complicated to explain here. But we have the paper. You can read the paper.
Oh, thanks.
Thank you for the talk. I'm also from the math side, so there's some questions where I'm trying to clarify my understanding. So first, I want to understand how this embedding works. My guess, based upon how everything's presented, is we're given a network. We have values on the edges. Based on that, and some combinatorial Ricci curvature type calculation, we can derive Ricci curvatures on the edges. And then using the positivity and the values of that, you either do clustering or and things like that, and fit it to heterogeneous latent geometries. Is that understanding roughly correct?
Yeah, I think that's a high level. Yeah.
Okay, thanks. So I've got a question about like potential hierarchical mixed curvature. So what I mean is, consider something like the phylogenetic tree. You have different processes happening at different timescales and at different levels. So, for example, you might have a spherical cluster type of curvature on very micro level scales, and then if you move up into like deeper levels or more macro levels of the tree, you might start to see hyperbolic types of curvature and things like that. Do you envision a way of capturing that sort of structure using these ideas?
You want to address this question?
So could you repeat it again?
Sure. Okay. So graphs and networks occurring in nature and life often occur as a consequence of multiple different processes. For example, things like phylogenetic trees, where we're trying to classify animals and things like that. Evolution is occurring at different processes. So you could have like a tree where if you just squint your eye, and then cluster everything and just make the clusters into single nodes, it looks hyperbolic. But if you look at the clusters, they look spherical. And something like that, if you just do the Ritchie curvature calculations on the edges, it'll go, most of this is positive curvature, most of it is spherical. But you're not seeing, and you'll have some hyperbolic maybe edges throughout, but then you're not seeing the upper level hyperbolic structure. Is this something that you guys envision possibly tackling at some point, trying to see these different levels in the actual trees?
Usually we do not use the hierarchical construction of the Riemannian manifolds. Usually we do not use the hierarchical construction. And usually for the evolvement process, we have a unified formulation with the Riemannian manifolds. And for the hierarchical, your hierarchical observations, I think it can be well elaborated in some single manifolds. We do not need the hierarchical construction. And for the evolvement process, for the Ritchie curvature calculation, we have some principled way for such for your purpose. Yes.
Okay.
So
okay.
and for some further details, you can refer to our III 2023 paper, and also there are some details in our SML paper, which I will present it in Vietnam.
Yeah. Okay. Thanks. And I've also got one last question. So this is about I think like this type of heterogeneous curvature idea is and Ritchie flow is very good for clustering, but I have some concerns about link prediction because when you actually compute these combinatorial Ritchie curvatures and then you're doing the embedding based on that, this is almost like you're overfitting a little bit because you're keeping you're saying, okay, I know that these edges, these nodes have a lot of edges between them. I know that these edges don't have that many edges between them and things like that. It's heuristically, it's doing something like that. So are there concerns of overfitting?
So basically for the clustering model, it is specialized for the class of clustering. Also, I believe the clustering, they have some connection with link prediction. For example, that the nodes reside in one same cluster, they have higher probability that these two nodes can be linked. So they have some relationship, but for our model for clustering, it is a specialized model for clustering. And if you want to use the manifolds to advancing the performance prediction, I think maybe we need to have another model. For example, our SML 2024 paper is for clustering, and we have the III 2024 paper for maybe the link prediction is as an evaluation task.
Okay, thank you.
Yes, thank you.
Professor Yu, I have a question about so in some slides you mentioned that we can use the tree structure to represent some network, such as Twitter. I think there is a number associated with network. I remember that Twitter is 3.5. I do not fully understand what the meaning of the number.
Oh, you mean the delta hyperbolicity?
Yeah, maybe. There is a number.
That is a measure seeing that how the structure is close to the tree. It's not a perfect trees, right? Nothing is a perfect trees, right? So that is a calculation, okay, to saying that how closely a structure relative to a tree. So, for example, if a tree doesn't have those cross edges, right? If you have the cross edges, then they become less like a tree, more like a full-blown graph, right? So it's just measure that kind of deviation from the pure tree. So this is what this delta hyperbolicity measuring.
Oh, okay. And actually, I have another question. Is still about the if we want to represent the maybe some relations in the Twitter data. I think in Twitter the network, I think it is combined of knowledge graph and social network because for the account, the Twitter account, it is actually the knowledge graph because there are some attributes for each account, each individual account, and there are interactions between different Twitter individuals. So how do we represent the maybe some complex?
Yeah, for any kind of network, there are all these different versions, right? But the kind of Twitter we are referring to is just the user connection. But they can have different relationships, right? Because you can agree on someone or you reposting someone, but it's basically the node is the user.
Oh, okay. Thank you.
Any more questions? If not, I too have some questions. You didn't mention the how's the computational part, like how many navida you calculate. Looks like the graphic network, the training needs more computational part, right?
Yeah. Certainly, it takes it's more complicated. It takes more time, right?
Could you give us an estimate how many, like, and if I need to train this kind of?
Do you remember how much is the complexity?
Depends on the size of your data set, or
like the Amazon, you have the free application.
For the graph of thousands of nodes, for example, the benchmark data size, let's say the Quora. For this, we can complete the experiments on a laptop. But for with the tens of thousands of nodes, maybe we need a little bit more GPU. It do not have basically the energy efficiency is okay. It's competitive to the normal for the Euclidean versions. It's competitive to Euclidean versions. You do not need to have times of the GPU requirements. It's just competitive with the.
Okay, so basically based on the how large.
It depends on the size of the data size, and it's competitive to the Euclidean versions. Yeah.
Okay. Another question. You mentioned these two applications, recommendation across network alignment. Have you think of other area that we can use your reach currently to this kind of?
But we can use for anything, right? Any type of thing you use this graph neural network, right? This is not just we are doing the same thing, right? It's just that anything graph neural network can use, this can be used. It's just that we are doing in a different representation space. Instead of doing in the Euclidean space, we are doing it in this Riemannian space, mixed curvature space. So any application it can work, will work, right? But generally we don't need label. So okay, we can just use contrast learning to solve the problem.
So that means we can apply this kind of method to any other fields.
Anything, yeah.
Anything that
can
by the graph.
Yeah.
Okay. Yeah. So I think lots of you maybe have later will add your WeChat communication with you.
Okay. Good.
Okay. That's a welcome, Professor. You again.
Thank you.